Mr. Hanson.
Thank you all. If you didn't happen to see my bio, I'm actually a lecturer in applied math in it's called the Computational Finance and Risk Management program. It's a terminal master's program within applied math at University of Washington. So it prompted me to mention two things.
Thank you very much.
One, maybe the folks at Volt might start hiring financial engineers too, hire some of our students. And then the other thing is, you see I've got Bart Starr here, and whenever I start a new course and I introduce myself to my students, you know, I tell them, you know, my background and all that boring stuff, and I say, but most importantly, I'm a part owner of the Green Bay Packers, and I love bad jokes. Okay, so I'm going to cover some stuff that actually it's sometimes being in the field that I'm in, which is quantitative development, is mainly what I teach. You get the feeling a bit of being like Rodney Dangerfield, you know, because they don't talk about math that much in the conferences. It's not. There's just not that much. I mean, occasionally there'll be the occasional talk or two, but there's a lot of stuff starting with C++ 11, which benefits those of us in math and more in particular in computational finance. And so that's mainly what I'm going to talk about. But at the same time, as kind of an overview, I also work a lot with helping to place our students with internships and permanent positions after they graduate. And again, there's just not a lot of demand for C++ people. The jobs are out there, but it's very rare that we get a student placed in one of these positions. And so it begs the question, what are we as the C++ community? Or, you know, could we be doing something better? But I'll get to that toward the end of the presentation. First, I'd like to just thank a couple of people. Daniel Shea was a student of mine and did some independent work on parallel STL algorithms, and so I took some of his results to put in this presentation, and also someone we work with somewhat closely now, Jared Broad, at a company called QuantConnect, which is an online service for backtesting and setting up trading strategies, has allowed me to use some of the graphics work that he put out on their website. Okay, so an overview. We'll look at some of the features and the new standards and how they help us in math and quant finance. And then also look at Boost. And there truly is some really good stuff, and there's some bad stuff, and there's just some clean ugly stuff. That's my opinion. But it comes with the experience of having worked with it. Okay, so the new standard. It's a good album, by the way, by Herbert. All right, so of course you all know about lambda expressions, and you know about the new parallelism that started with C++ 11, and of course parallel SQL algorithms. But how many here have actually worked with the random number generation that began in C++ 11? 3 guys.
Good stuff.
Yeah, that's right. That's a good stuff. Okay, so there's some interesting applications of that where we can use all of these features. So, but they're just, as I say, probably things that you might not have seen yet, that you haven't seen before. Okay, so first we'll look at random number generation, and then as part of this I use lambda expressions. Everybody knows this, so I don't think I have to go into it, but to see how they can be conveniently used mathematically. And then we'll close out this section with how to generate equity price simulation paths. And then after that, then that gets used in the next section for pricing options. Okay, so the way the random number generator works is you have an engine and a distribution. So what the engine does is it's going to generate a large number of integers from, I don't know exactly how they do it, but I think it's some kind of extended uniform distribution over a large range of integers. But you can, in the past when we had to write these ourselves, we'd start with a uniform generator on 0, 1 and pick real numbers. But the way they do it is they use a sequence of integers. But it doesn't matter, it's all topologically equivalent. So anyway, you generate these integers and then you apply a distribution. So that is the transformation to the distribution that you want to use. For example, normal distribution, binomial, exponential, whatever it is you want to use. So for the normal distribution, it uses the well-known Box-Muller method. And again, what I want to stress here is that before C++11, well, first of all, this is a very, very common task that you have to do in finance, is to generate random numbers in order to set up a Monte Carlo pricer for options. And so, you know, I worked several jobs in the industry, and it seemed like every time I went somewhere, the first thing was, you have to do that. You have to start from scratch. Now we don't have to, and it's wonderful. I mean, when this came out in C++11, I was really doing my happy dance. Okay, so in a picture, this is what it looks like. So the engine is going to generate positive integers. Then we apply some kind of transformation to transform the statistical distribution that we want to use. And then if you're using it, well, what is the, in C++11, what it will do then is generate random numbers from a distribution. So give it a seed. And so at the end, then you get just a sequence of random numbers. This is an example from the normal distribution. Okay, so there are, though, there's a nice set of distributions that are ready and waiting for you. Among them, the uniform distribution, typically on 0, 1, like I mentioned before, you select just real numbers from 0, 1. The Bernoulli family, which would also include the binomial distribution, Poisson exponential, and the normal family, which is not from whence I came, but it's another story for another day. But anyway, the distributions that are related to the normal distribution include chi-squared, Cauchy, the student T, and the F distribution. So, and they're even more than this. So, what will be interesting to see, though, and this is an area that I've done some work in at the university, with some more advanced distributions, especially for finance, where you have to be you want to be able to capture the skewness and kurtosis, which you can't with normal distributions. And there's some advanced methods that have been published. One in particular I've been kind of associated with. And it would be interesting to investigate if there's a way to integrate those into the platform we have here. I just thought of that standing up here. So anyway, I better not push my luck, but it's just something that occurred to me. But if the base library exists, would there be opportunities? Well, the other thing would be to propose them to the committee to see if they might accept some of these into the future standard. Okay, so here's a simple example of just generating some random numbers from a standard normal distribution. The first thing we need to do is set up our engine. And there are a number of different engines you can use. The one that is the most powerful out of all of them is the Percent Twister engine. And it's the one that's preferred in production in finance. So if what we do is, this is the name of the class, so we create an MT object, I just call it MTRE, for Percent Twister random engine, and then the argument is the seed, so just 800. And then once you do that, then you just call it as a functor, and then this will kick out randomly generated large integers. That doesn't help us so much, though. What we really want is the normal distribution. But what we do is we're going to take these numbers, and then they're going to get transferred to random variates from a standard normal distribution. And the way that's done is we create a normal distribution object, which you see here. No arguments, unless if it's standard normal, it's a default 0, 1. If you want to put in the mean and standard deviation, then you would put that in the arguments in the constructor. And then it's just a case of taking the MTRE object, which we created earlier, and sticking in the argument for the normal distribution functor, and out pop random standard normal variables. So it's very easy. Those of us in quant finance really like this because it's so simple. It's just there. You can get on with the job, which is really, really nice. Just as a side note, the default template parameter is a double type, so it's just typically left out. In my C++ classes, I teach it for again for computational finance, so I spend about 2 minutes on the different types, and in C++, and I just say, all we care about in this class are doubles and ints. That's it. Let's move on. But I know that's a different focus from what a lot of other people use it. And, I know in data science where they're having to, all these different types, it give me nightmares. But in finance, we just try to keep it simple. Okay, so again, very, very common task in quant finance is to generate paths, simulated paths of equity prices. And there's a well-known result that comes out of what's called toe calculus and Brownian motion, which gives us this nice equation that you see here. And the arguments are going to be the previous stock price. So it could actually be what's observed in the market at time 0 or the next step in the simulation. R is the risk-free interest rate. Sigma is the standard deviation of the stock price movement. Delta T is what we're going to do is we're going to, is it okay? Is there a marker here? Yes, no?
Checking the desk. Checking the desk.
I should have checked this one. If not, it's not the end of the world.
I can grab something on the slide too.
It's okay. What it is you're going to have a time period from 0 out to some terminal time t, say 1 year, and this is a result from what's called stochastic calculus, and so this is an approximation to, remember from calculus dt means a very, very small increment. So we have to chop it up into small bits to make this work. So that's just a discretization of the result from stochastic calculus. Anyway, but all those values are known. The only thing that's not known is this, come on mouse, there you go, is this epsilon t. And that is what we get from the standard normal distribution in C++. We can just, those are random variables. And so we're going to just choose a large number of them and stick them in that equation. And then as you compute this, then you get a simulated path of equity prices, which somewhat represent reality because you're using the volatility of the, or the standard deviation of the stock. Just in case you might be wondering why are we using the risk-free rate instead of the mean return of the stock, that's because the next step of this is to apply it to options pricing. And long story short, there's a mathematical theorem that says we can change the measure, and so we can just use the risk-free rate. It's based on what's called the arbitrage-free theory. So, but the upshot here is that everything is known. All we need are those standard random, those standard normal variates, and we're done. So again, this is really, really beautiful. It's so simple that even a quant can do it. Okay, so just to look at the class I put together, equity price generator, it's going to return a vector of stock price, of random stock prices, of simulated stock prices. And then if you look in the implementation, as you can see, I've noted here, this is where the magic happens. And so, as before, we set up this engine based on Mersen Twister and a standard normal distribution. And then we can also bring in a lambda expression, and this is where we implement this equation here. So now lambda equations come in, and these are beautiful too because this could be just a one-off thing. We don't need to write a function that's going to be exposed here. We just need it for this one task, and it's a mathematical function. Just put it right there and call it. So all you have to do then is it's just a simple loop, but we're just going to generate equity prices. This is the previous price. This is the epsilon t, and the year fraction, the delta t. Then this calculates the next equity price, and then we push it into the vector. That's it, and we're done. Okay. So if you were to plot this out, this is actually done in Python, but that begs another topic. But this is what it would look like if you were to plot them out, say 10,000 simulated paths. We start here with an equity price of 100, and then you can see that it is randomly varied. So we're simulated paths of equity price increase. Okay, so this feeds nicely then into the next topic, which is Monte Carlo option pricing. And I guess now I think with the slides I can do it. I've got an eraser here. Eraser can mark it. I think I can explain it. Anyone know this album? Come on,
Yes, going for the one.
All right, you are a winner for the day. The duck should be coming down from the ceiling. Say maybe a few of you get that reference too. This is really.
I suspect brief.
What's that?
I suspect brief.
Yeah, well, Maybe
I
a
do.
rerun. No, I love talking here because, when I teach, I love my students, don't get me wrong, but, I try to make some reference and, duck or whatever, and then so I'm among friends. So, anyway, oh, thank you. Thank you very much. Okay, so what is an option? So the easiest, the simplest type is what's called a European option. And so you're going to have the stock price along going, these are simulations. But all we care about is the terminal price that we get in our simulation. Then there's also what's called a strike price. And that's usually called K. And so when we get to expiration time big T, we can exercise this option. What it means, there will be a payoff, and there are two types. One is called a call, and the payoff is going to be max of the terminal price minus the strike or zero. And put is when you're betting the stock is going to go down, and that's going to be the other way, max of K minus ST and zero. So, but this is at the terminal price, big T, not at time zero. At time equals zero, if we wanted the present value of the payoff, we would have to discount it, and that's going to be e to the minus RT, which is this is just a discount factor. All this is doing is discounting from big T back to time zero, and then it's going to be whatever the payoff is here. So that's the present value of the payoff of the European option for one scenario. What we're going to do is we're going to do this 10,000 times, and then we add them all up. Some of these may be zero. That doesn't matter because those are possible prices. And then we divide by the total number of scenarios, and that gives us our option price. So, what we need to do is generate a bunch of equity path scenarios. And this didn't have exactly the scale I wanted, so pretend that's 100, and that's 20, and that's 40. So this is our strike price. If this is a call option, then there are only two scenarios here that are actually going to pay off, or they're simply in the money. So there will be positive payoffs there, the rest will be negative. But we sum up, this is going to be, so we'll have a payoff of $30 here, of $10 here, and 0 here. So it's going to be 10 plus 30 divided by 5, which will give us our option price. That's very simple, so you can actually see the scenarios. Well, what we really need to do is generate a whole shipload of scenarios. And so we're back to our freaky Jimi Hendrix 1970 style picture. Talking about Purple Haze, man. So if we set the strikes at 110, and this is a call option, our positive payoffs will be above this line, and then below this will be 0. But we're almost there because we've already generated these in what we did already. So that part's done, and we're C++ programmers, reusable code, right? So it's already done. So now we can do this. Going back to this, we can now go scenario by scenario and calculate the discounted payoffs. But we have now built-in task-based multi-threading. Again, it's so beautiful. Forget p-threads or this other stuff. It's all in the standard. You can compile on Microsoft. You can compile on Linux. It doesn't matter.
It seems to me that instead of running the simulation over and over and over and over again and summing the results, you could actually mathematically directly calculate what the average of all the simulations will be, since you know the algorithms involved. So I guess
You mean like
I
using
don't
Black
really
Scholes?
What?
You mean like using Black-Scholes?
I don't know what Black-Scholes is.
It's a closed-form formula for pricing. Yeah.
Okay.
But the reason I'm talking about this is the world's simplest example. They get far more complicated than this. And when you start bringing in hybrid FX and interest rate derivatives, these things become highly complicated, and so you really have no choice but to use Monte Carlo simulation.
Okay.
So I'm just showing a basic version of it.
Okay, so there
Point
is a
taken.
closed form solution?
There is, yeah. It's called Black-Scholes.
Okay.
So what we can do, though, is we can take each one of those paths, and we can generate those, do all the generation and everything, and in different threads. So and we don't have to care about what the others are doing, because this is an embarrassingly parallelizable problem, which again is beautiful because we don't have to care what is happening on any of the other paths. We don't have to worry about shared memory. So we can use task-based parallelism using stood future and stood async. It's a no-nonsense and very straightforward solution in C++. And one thing that I've noticed, though, is that in the textbooks and in other courses I've seen, when they talk about multi-threading, when they introduce it, they start hitting students with actually managing the threads on their own. And again, this may be because the audience I teach to, we don't have to care about this, and it's a case of why mess with that when we have task-based parallelism? Just do it. And as Myers points out, it can actually be more efficient. Certainly less error-prone and as quickly implemented. I'm not downplaying the need to study proper threading, but hitting students for the first time who've never had C++ before, now with all the, oh geez, I got to think about these threads and all this. Well, no, just do it task-based, learn that, and then go on. But that's, again, just my opinion.
So Dan, so to be clear, because I know Herb Sutter's talked to this very group in years past about how the traditional low-level, threading models with mutexes and the condition variables and that thing is not the right abstractions for your typical developer. And we should be thinking of very high level, and that's really what you're saying as well.
Basically, yeah.
Okay, I just wanted to be clear with what your point was there.
Yeah.
So we shouldn't be messing, because I agree with that. I mean, in general, the average developer shouldn't have to be dealing with where do I mutex locks here, where do I condition variable there, where do I, signal this and that.
And in this case, we don't even have to care about mutexes because it's all Myers and parallelizable. So, we don't even have to talk about it. So, but that's in quantity. What it really boils down to, I'm happy that I'm on the same page with Herb Sutter, but
It's not though, that's a common discussion.
can I use that though? Now name drops it. Oh, Herb Sutter. What I tell my students is it comes down to what I call the laziness lemma. If you don't have to do the work, don't do it. Okay, so this is just an excerpted look at the header for what I call equity price generator, and you'll notice, let's see, no, it's actually in the implementation, but there are two options to calculate without using parallelism and with async, which would be in parallel. We have to generate each seed for each scenario, because if you repeat it, then you're just going to get the same numbers over and over again. I also have a timing function here so we can compare running parallel versus in serial. The main part of the implementation is, you can see at the top here, here's our equity price generator class, which we set up in the previous section. Oh, you got a question?
Yeah, quick question on the parallel part. So is that accounting for parallel run of the algorithm, or what was the...
I'm sorry?
So you have two functions, parallel and non-parallel versions.
Yeah.
What's the parallel for? Is that to run the function?
The parallel version will run what you see here.
Okay.
The non-parallel version is not shown, but we're not going to use async in futures.
Oh, okay. Just got it.
So, actually, it would probably. Okay, so before we get to this function, we have created a vector called seeds. So this will have different seeds. I just did it using iota and counting them up, but it, whatever we want to do. At one company I work for, we use the account numbers of policyholders as the seeds. So, but it doesn't really matter as long as they're different.
Sorry, as like a privacy engineer, it's like it's cringed massively.
Oh yeah, no, it didn't. It was all in the database.
Yeah, that doesn't make it okay. That doesn't make it okay.
On the other hand, don't blame me. I didn't make the decision. But it's all there. It's all there in the data that's being brought in anyway. So there's no risk of using them. The presence may be. Don't get me started on actuaries. Okay, I got to tell this one. Two actuaries are talking to each other. How can you tell which one is extroverted? He's the guy that's looking at the other guy's shoes while he talks. Okay, so what we do is we create a vector of futures, and so this is just going to take in the equity price generator functor with the seed argument, the one seed argument that it takes in. And so now these are all being put out, they're all being run in parallel behind the scenes. The generation of each scenario, it's all being done in parallel. So then when we get done, what we want to do is get the discounted payoffs. And so we're just going to now go through this vector of futures called get, which is going to get the result from the future object. And since we only care about the terminal price in this case, again, remember this is the world's simplest example, we only want the terminal price, so we just call back on the object that gets returned here. And then let's see, this is, calculates the, okay, then there's another function which you don't see, which is going to do the max function. It will depend on whether it's a call or a put. And then those results will just be put into another vector of just the terminal discounted payables. Yes, sir.
Any specific reason why you have double terminal price and then do payoff underscore terminal price?
I'm sorry?
The line about terminal prices in the future get back,
Right.
and then you have the terminal prices next line. Is this just a reason for that? Or?
Yes, because this, I'm sorry, this terminal price is this at the end of the scenario. But we need now to take this and input it into the payoff. So this object will know whether it's a call or a put. There's I don't know if you saw in the header. Okay. So it will know which one of these to choose, does this calculation, and then at this line, then it's going to apply the discount factor and discount it back to 2%. So then we just calculate the mean, and we're done. So I just ran some comparisons, looking at serial versus parallel. So as you can see, starting out 12 time steps, 1 year period, there's no difference. But as we go along now, especially as we get up in this range, we're cutting off nearly half of the runtime, and that's on just this little bitty, what do you call these things? Surface. So another follow-up project that I'd like to do is run this and then actually run some more complicated types of options on more robust machines and see what kinds of differences we get. Okay, now you may have noticed here I've got a 5-year option and a 10-year option. If any of you, yes?
Sorry, I'm just wondering what was your parallelization factor? So like how many threads were you trying to run? It looks like 2, but...
Probably, yeah, because it's just this...
Yeah.
I'm not really sure what this has in it, if it's two physical, 2 virtual. I'm not sure.
Okay.
But it does look like that.
Yeah, it looks like 2 based on the numbers.
Yeah. So, but that's what I'm saying though. It's just my little bitty surface. So you can imagine if we had a meteor machine.
Yeah.
And then on top of that, as I said, you get some of these really complicated products. And back 10, 15 years ago, you'd have to have a farm of servers to run these things overnight. Yeah.
It seems also like an ideal application for a GPU or the XMM registers, where you could get a lot more parallelism, but without using multi-threading.
Right. Yeah. That's the student I mentioned. He had done some work on that, so that would be another topic for another day.
Okay.
And you had a question?
So you're just throwing away everything else in the factors?
Right. For this case. But you can have options where like what's called a barrier option. So that's what's called up and out. You set a barrier, and if you hit this barrier, then your option expires worthless. So now you do have to care about what happens in between. And then there are Bermudan options. American options can be exercised any time before expiration. So again, this is just very simple. So, but what I was getting at here is, if you're familiar with finance at all, you might be scratching your head here. What, 5-year option, 10-year option? Can't, those aren't traded. True, but again, when you get into some of these more complex products, they can go for 5 years, 10 years. Things like swaptions, interest rate and FX swaptions. Again, the interest rate and FX structured products, caps, floors, and then there's a whole, I'll talk about working in insurance, it's the variable annuity field where these products can extend out 30 years. So it's not that option, but there's essentially an embedded option in these products. So, but the underlying concept is the same. You have to generate these scenarios, both for payoffs. So, but the upshot here is that C++ gives us power, speed, and scalability, along with just something that is so dirt simple to implement right away. And but the word just doesn't seem to be getting out. And but again, that's kind of the dilemma that I see. In the old days, before we had these, some of the actuaries would insist on using Excel and VBA, and I'd be getting up to leave at 5:30, and they'd still be working. What are you doing? Oh, I'm running some scenarios. So we're using VBA. It's like, well, I use C++. I'm going home. So anyway, you've seen the results. I mean, this is just on my simple Surface Pro, getting cuts of about 50%. Again, I'd like to, next step is to look at this on higher performance machines, also GPUs. So, we're working on it, so stay tuned. But again, it gets back to this open question about why do textbooks and reference books, they seem to be stuck in the past by ignoring this very powerful tool. And I just find it kind of perplexing. Yes?
I think it's the same reason why a lot of companies and groups have moved away from C++, because it's harder to get into at the beginning, but has all these benefits on the back end. So, you go learn Python or something like that, and you can immediately start running whatever you want to do, and it's very easy and simple, and all the libraries exist, and you just sort of go do it. Whereas in C++, it's sort of a do-it-yourselfers type of language where you have to learn a lot to do.
There is that, but I'm going to get in that in a few minutes. But as Sturstrup himself has said, C++ has a public relations problem. So, and I think that's a lot of it. A lot of this I don't think is all that difficult, but I think the way that it's taught, it's made to look difficult. It's just kind of, so.
I just wanted to continue. Yeah, that's certainly been my experience with academia and C++.
Yeah. So. Okay. Speaking of whom. Okay. So parallel STL algorithms. So introduced with C++ 17. As I understand it, only Visual Studio is the only major compiler that has this nearly fully implemented. Is that still true?
GCC just recently,
9.1.
9.1 is
okay, so
in cooperation with Intel and Intel EDB.
Okay, so GCC now has gotten it.
Just
It's just gotten it. Okay.
You might have to compile it by hand, but sure. It's really easy.
Okay. Well, again, the laziness.
Intel had.
Yeah, okay, the laziness lemma, use Visual Studio. So I think you probably know about this already, so I won't go through it, but what I did is I did an example comparing the first two. And also there's some, again, you're probably familiar with these, std reduce is essentially a parallelized version of std accumulate. So that can be.
You forgot Clang.
What's that?
You forgot LLVM and Clang. That does support the latest in C++ tools.
Clang does now?
Sure.
Really?
This is one area where MSPC was ahead.
I know that last year we had a compiler group come and their head of one of the guys said, yes, C++ 17 has been implemented for Visual Studio.
Okay. Oh, with parallel algorithm STL?
We didn't discuss that.
Okay. All right. So anyway, additional information, some good information at this URL. So what I'm going to do in this case, this is kind of a contrived example, but it's not too far away from real-world computational work. So I'm going to look at an example with std transform in serial and in parallel computing. But again, it's one of those things that it's just so easy to make this little tweak, and you're done. And I guess that kind of gets back to what we were talking about. Why doesn't the C++ world push this? You can do these things. That'll give you significant improvement, and it really doesn't take long. But I digress. So again, this is kind of a contrived example, but what I'm going to do here is take a very large random sample from a standard normal distribution. And then for each value in the sample, so I'm going to put that into a vector, and then at each point in the vector, I'm going to compute e to the x using an approximation to the infinite sum expansion. Let's see what happens. Okay, so this lambda just implements the sum. And so we start with a, actually it says v, but I'm using u here. Okay, you might correct that. But, in the first case, we're not using parallel STL. Now here we are, and all we have to do is just add this this one argument. That's it, and you get major improvement. So the vector u and the vector v, these contain a very large number of standard normal variables. So the idea is to keep the processors busy for them. And then at the end, I calculate the mean just to make sure that there's a sanity check, and then look at the time that it took to complete each. Okay. Maybe I should redo this chart, but I did it to fit the page here. So again, you see on the order of 50+%, so it probably is just two processors at work. But again, just putting in that, does everybody remember the Monty Python meaning of life? Was it creosote? It's a perfect thing. You just put in that little argument, and you get on this little computer 50% cut Monte. Any questions? All right. Rant time. Actually, I had a, hey, that was good. If you do a little louder, we'll catch it on too shy. I'm going to concentrate mostly on the good, though, but have a few words about the bad and the ugly. So, an overview of Math and Boost. There is the Boost Math Toolkit, and then there are some additional math-related Boost libraries that are not in the Math Toolkit. Some of these can be very useful. So, Statistical Distributions, I'll talk about that in a minute. That is a nice extension to what's in the standard now with the random number generation. Mathematical constants are convenient. It may seem like a little thing, but it's a nice convenience. And numerical integration, which I think they did really, really well in Boost, and I think should really stand as an example of how to do it right for other numerical routines. Then some additional features, circular buffers and multi-array accumulators. These are all very useful, and I cover these in my advanced class for finance, because we can use these very convenient. There's an ordinary differential equation solver. I have not used it. I've heard good things about it. I just haven't used it. In finance, it's more concerned usually with partial differential equations. So anybody want to write a PD solver? Any volunteers? Okay, we have a volunteer.
I do
Oh,
it.
we got two of you, all right. Okay.
I have done it.
Oh, you have? Okay. Cool. Well, let's look. We're cool with you. And then UBLAS, I have some words about that. And then there's some features that have been migrated from Boost into some of the new standards, which is really, really great. One being the number generation, which we'll talk about. Also special math functions, so Bessel functions, so you have polynomials, I'm sure you've got those memorized so you wouldn't need this. And then these are kind of convenient, greatest common divisor and least common denominator. So a little comment about least common denominator. I always hate it when politicians talk about it. And he's pushing us down to the lowest common denominator. So wait a minute, lowest common denominator is a good thing. All right. So, opinion. And again, I like this crowd because you probably know who that is. But in my opinion, there are some really, really good libraries in Boost for you. But there's some that are just poorly designed or dated and neglected. We don't even know if they're being supported or maintained anymore. And then the ugly are the ones that are just so over-designed to the point that it takes way too much time to figure it out. And again, you know, quants are busy, and they got traders yelling at them and stuff like that. They don't want to have to take time to look up the latest and greatest super-duper template pattern from hell, right? They just want to get on with the job. And I think this is where some of these fail, and I think this is why one of the reasons too that C++ in general can get kind of a bad rap. But that's my opinion. Okay. So we could talk about math and Boost for an entire lecture, but can't. So actually I could talk about it for half a day. So I'll focus primarily on the good, but then how Boost could be even better. Okay. So in Boost, in the math toolkit, I mentioned these three features. Quadrature is numerical integration and differentiation. And then these, again, were migrated to the new standards. Okay. Just quickly, mathematical constants. We often have to deal with pi and e and various variations on that theme. So rather than put in 3.1415, you know, we don't like magic numbers, right? These are defined a priori in Boost at compile time. So we can just use the symbols, and it also saves us from using god-awful C-style macros. Yes?
So the constants in there, are those out to full precision, basically, or are they?
I don't know how far, I need to check. They've been sufficient for our purposes, but I'd have to look that up. It's a good question. What's the precision? I think they're double. So you can get the comprehensive list here, but this might be a little bit hard to see. But for example, square root of pi is used a lot. So just put root pi, and then it also saves too, arguments with coworkers. There's always that one guy says, well, no, we should carry out to 17 digits, not just 16. And then you get an argument, and then your manager says, okay, you two come in here, and 2 hours and you need to settle that argument. It just takes crap like that out of the picture. Yeah.
Well, I'm going to be a little argumentative.
Okay.
Wonder why not use the 80-bit reals instead of the 60-bit? I mean, instead of the 64-bit doubles.
And use what instead of what?
The 80-bit ones. Intel CPUs have support for 80-bit floating point numbers instead of the double precision, which are 64-bit.
That could be. I'm covering what's in the standard or near standard. Okay. So that's Boost, and I'm in academia, so we don't have all that money, so we stick with what we can get. Well, at least I don't get it. I don't have tenure, so I don't get much respect. My doctor told me to start smoking, so I quit chewing gum. So anyway, these are convenient. So okay. Now, statistical distributions. These are beautiful. Again, we use these a lot in quant finance, and they're used in applied math quite a bit. And it's very simple. It's just like you would, as if you're writing out in math. You want to use the student's t distribution. What's the parameter for the t distribution? Degrees of freedom. Class name, object, degrees of freedom. Done. Beautiful. Same with the normal. This is standard normal. That's 0, 1, but you can put in whatever mean and variance you want. But again, just the instantiation is very easy. No templates to, at least that you have to worry about, fancy design patterns. It's just, you just use it. And then once you create that object, then the member functions are PDF. See, well, these are these actually take in the object. So the density function, distribution function, and quantile. So you just pop in your object that you created, previous page, and then the quantile that you want, or the value, CDF or PDF at some value X. Again, very mathematical, just flows very nicely in code. There are a lot of distributions to choose from, which again is nice. And there's some in here which actually are four parameter distributions. There are a few, which is very nice for finance. But again, it would be nice if they're, again, just a thought, to make it easy for people to submit new distributions. So, but that's,
Okay.
what's that? The K distribution? I'm not familiar with that one. But you got me on that one, Doc. Okay, let's, with luck. With luck.
I built a K distribution on top of these.
Oh, really? Very cool. I like it. Love it. Okay. So, but in practice, what we usually need are, for any distribution that we're going to use, we need the PDF, the CDF, the quantile, and random sample. So Boost gives us the first three, and then the last one is now in the standard. So the question is, might we see the first three make it into the standard library too? Be nice. Now, numerical integration. This is an example of, I think, how the other math functions in Boost should really take a cue from this. This, again, is so beautiful. If we just look down, let's just look ahead here. We're going to use the trapezoid rule to integrate a function over the interval 0 to 1. How easy can it be? Just use the trapezoid rule on that function, limits of integration, done. And not only that, not only can we use a lambda expression, we can also stick a functor in there, either one. So again, it flows very nice mathematically. Now, what I'm talking about is, when I talk about the others, there's part of the Boost Math library that does root finding, and I cannot figure out how the hell to use this thing. It's just, it's my opinion, but it is just so over-designed. You could do something exactly like this. In fact, I teach this as an exercise. I say, use the secant method, which will take in a functor. So, I mean, if my students can do it, the people at Boost, I think, can do it. But anyway, back to our story. Again, this is really beautiful. This function, if you integrate it from 0 to 1, you get you get pi. And so you can use the default, or you can also put in your own tolerance, or max refinements is, I think, a limit on the number of iterations. So again, it's beautiful, just works right out of that. There are other numerical methods available for integration. And differentiation is also available using first finite difference. But this is just so cool. And as I said, this really is an example of a very well-designed library. Circular buffers. A number of the audience here taught me about these. And since then, I found them to be very useful for time series. I'll just go through some of these quickly. But it's essentially, it's like a stood deck, but with fixed length. So you tell it a priori how long it's going to be, and then it will, as once you fill it up, then when the next value comes in, it's going to pop out the oldest one at the front. So it's very, very useful for managing time series data. Multi-array is very useful. You could have another way of pricing options is to use what's called lattice. And the way this works, you're going to start out at some point, and again, this is the stock price right now. And so you're going to go out. There's probability up and down. These are determined by theoretical arguments, just so you accept them. And it's going to keep going, but it recombines. Actually, this should be out here more. And as it keeps going out, each of these now is going to represent a time scale. And what you do is it's kind of like the random number generator, except this depends upon the probabilities that, again, come from, they're not empirical, they're actually they pop out of the theory. But it doesn't matter. Again, it's a change in measure argument. If you're familiar with that. Anyway, what you do is you generate the stock prices going out, and then you have the payoffs, and then you're going to take those expected values, and then they're going to collapse down into the value of the option here. Well, the reason these are really useful is that a multi-array, so this is just in 2 dimensions, but each one of these can be an object or a struct and hold that information. So what's the stock price going out? And then it can hold the expected value coming back in. That's a very simple example because I'm assuming constant interest rate. In fact, you could just do this with a single factor here. But again, as option products get more complicated, you need to hold more information and more things can happen at each of these nodes. So it's very useful for that type of application. And also these can actually be 3-dimensional. I don't know if I can draw it, but they kind of, we have things like this happening. That makes sense. They could be in 3 dimensions, they could be even more dimensions. So that's a useful tool to have. Accumulators will give you basic descriptive statistics on a set of data. So mean, median, standard deviation, the usual stuff. As I said, the ODE solver, at some point I'd like to investigate it, but Doc, you and I will talk about getting this summer. Think we get done this summer? Okay, now comes my opinion. See, I put good here because these are all good, but I've used this, and I'm sorry. This is my opinion. I've used it, and this is an example of ugly. Just to multiply 2 matrices Yeah, go ahead.
Have you joined the SG14 linear algebra discussion yet?
I didn't know there was one.
Well, there is one, and we're talking about how to integrate all these tools to make a fantastic
Ava.
linear algebra
Yeah,
library.
no, I did, and that was one of the things, I've heard rumblings that linear algebra is going to go into a future standard, which, again,
So it's part of
What are the-
SG14 and SG21,
okay.
or whatever the continuing education. The
Okay, thanks, yeah. No, I'll look into that. That would be great. Yeah.
I have to say, I agree with you on UGloss.
Yeah.
I've looked into it, and I think it hasn't been touched for a decade.
And that's the other thing too, it just, yeah, I don't think it's even being maintained anymore. And then, subsequently, along came two very nice open source linear algebra libraries. One is Eigen, one's Armadillo. Personally, I like Eigen, but they're both very good and they're widely used in finance. Okay, so summary and conclusion. Had to get it. St. Vince, the patron saint of football. Okay, so the way we learn. This is true. I should look at the screen or look at this screen, but it took me till the end of the presentation to figure this out. So again, speaking from my experience, this is when I was actively working in the private sector. From around 92 to about 2006, C++ really was the go-to language in quant finance. It was just hands down. If you had any kind of quant finance project, it was going to be ultimately implemented in C++. But then Java and C# moved in. Some people thought, okay, they're fast enough. Development is, you can more rapidly develop things. Database connections tend to be easier to set up and actually can be quite fast. And there's less of, at least a perceived risk of memory leaks and program crashes. Also, some open source math libraries started to pop up for Java. And I actually used some of these because I was a client who wanted Java. So this is toward the late part of the 2000s. And I could just go, the National Institute of Standards had a very nice, just basic linear algebra library. I just pop into Java and I was done. I looked for stuff like that on C++. There's UBlast, but there's just nothing else. Or there were things, but I just could never get them to work. There's lousy documentation, so I gave up. But this is nice and neat. There's C#, .NET. There's a very nice library called math.net. This is the result of a merger of two different libraries. And then Python. Now this is a language, this gets back to, I can't remember what the Lloyd part of. Yeah, that these guys did it right. Said, okay, there's a Python language, but we're going to design these libraries, NumPy, SciPy, Pandas, scikit-learn. And they're like what Boost should be, in my opinion. So they're not part of the language, but they're kind of de facto, or the closest standard you're going to get without being in the standard. And again, I'm kind of jumping ahead here, but I think if C++, if the powers that be would make this more of a point of emphasis, then we could be competitive again. Yeah.
Do you think there'll be an increase, and is there an increase in demand for C++ programmers largely due to the increase in high-frequency trading that's taking place?
Yeah, I'm getting to that.
Okay.
But that's more of an IT side issue rather than quantitative.
Okay.
So, and what we're seeing demand for our students is a lot of them want Python, or they just say straight out, if you don't know Python, don't bother applying. I'll talk about that in a minute. So .NET also grew in popularity, and there are some very nice things about it. One nice thing though about C# is, I know we've had this discussion about the date class, but they did something really unique. They put a date class in standard C#. Wow, that's wonderful, because we have to use dates all the freaking time in finance. But in C++, you'd have to design it yourself, or you use the boost dates. That's another kind of ugly one. So we finally have one in C++, which is nice, but it took until 2020. But I think this is one of the reasons that C# started to become more popular in finance, because they had these things ready to go out of the box. There's also the ML.NET machine learning library, which is now open source and can be used from any .NET language, which is pretty cool. Okay, so the way we are now, okay, the beast is back. I mean, that's pretty cool. C++ 11, John Kelb out there, spreading the gospel. Got, a lot of these nice new features that we've already covered. And then as we went on, new additions, finally a date class in C++ 20. And correct me if I'm wrong, but at least I've heard rumblings that GPU-enabled parallel STL algorithms are going to be coming in C++ 20. Is that true?
I've heard the same rumor, but
okay, so
don't know if it's true or not.
Okay. And also, there's a greater availability now of quality math libraries, Eigen Armadillo, for example. And then in the machine learning world, CNTK, TensorFlow, and some others. That's the one that Facebook has. I can't remember his open source. What's that?
PyTorch.
PyTorch. But there's the Python connection. It's a hybrid Python and C++.
No, PyTorch has a C++ interface now.
Right, yeah. But notice Python, this is everything.
No, it's C++ underneath. So it's,
right, yeah, I know. But
you
play
bypass the
nicely
Python
together.
part.
And I think also that's another opportunity that, well, it's on the next slide, but that the C++ community should embrace is standard interfaces between different languages. It shouldn't be that hard in the year 2019 to call C++ from Python. I don't know, because I've not done that.
I have. It's gotten a lot better.
It's a lot better now. Yeah,
It's really pretty slick.
Yeah, I use R a lot, and there is a nice package called RCPP, and it plays very nicely with C++. But that could be yet another separate presentation. But don't worry, I'm almost done. You can see by the garden. We're almost done. Okay, so, but on the other hand, it's, again, the word we get from potential employers, it's very rare to have them specifically want C++ quantitative skills. They will often ask for one of C++, C# or Java. And so what I tell my students is that, okay, if you know C++, you can pick up Java and C# pretty easily. I say that from experience. Going the other way, not necessarily so. So you might as well, learn the best. And C# and Java are very big as platform languages, and some of the trading firms and investment banks, consulting firms, and so forth. And Python is for both prototyping and as a general purpose language is also very big. And then these are some of the common gripes that I hear about C++ is that, first of all, I've talked with head quants at financial institutions who have just told me that there are just too many different ways to do the same thing in C++. And it's true. What I try to do when I teach is to try to filter out the noise and get to, so they don't get too overwhelmed again with so many different ways. So, okay, we're going to stick with it this way, and you're going to be able now to go from step 1 to step N and actually get some work done. Also, they say C# or Java can be sufficiently optimized, and one head guy told me, he was in Chicago, in his opinion, going to C++ first would be a premature optimization. They favored the prototype in Java or in Python, primarily develop in Java for production, and then C++ if they need it. And then there's some, I'm not kidding, they're still afraid of the dangers of pointers and memory leaks, and they don't want to deal with bugs. Well, we've got this beautiful thing called unique pointer, and for most quant applications, that's all you have to use. Yeah.
And the other thing, in my experience, at scale, Java leaks and has more memory leak issues than C++ does.
Right, yeah. And those are the things that, I think, if we're going to sell C++, we should.
Yeah. Just dealing with it at scale.
Sure, that's true.
There's no comparison between
Right.
Java and C++. C++ is so much easier at scale.
Right. And also in the machine learning world, a lot, it's been a while since I've been involved in it, but a lot of the platforms now are on either the JVM, I hate using this word, ecosystem, or the .NET, the .NET platform. So Microsoft is definitely ascendant in the data science field. But now, I think we were talking about this too. This next point is that C++ certainly is dominant in trading firms for order execution systems, passing information, messaging, because they've got to be as fast as possible. And even when we think of high frequency trading, it's not necessarily trading down to microsecond. It's getting out first before the proverbial fit hits the sham. Okay. So a lot of the trading firms, they'll use the other languages, but when they're actually going live on the system, it's going to be C++. But this is more on the IT side. This is not something the math people don't deal with this so much anymore, or in some firms. There are other firms that have committed to it. And they say, yeah, it's a better language and we're going to make the commitments and the investment. But there are others who have these gripes. And again, I just haven't seen a lot of emphasis on quantitative programming at any CPP conferences. I've been going the last 4 years. And as I said, the creator himself, this is how he answered one of my questions when I was asking about why aren't we seeing more demand for C++ programmers coming out of the program. Okay, so how do we get our mojo back? Clean out the Boost math library and replace it with well-designed mathematical functions, much like what we saw with the Trapezoid method for integration. And then look to Python for what they've done, and in Boost build up something similar to NumPy, SciPy, and some of these other libraries. Or if some of this stuff is going to go into the standard, then, as I say here, make it SEO number one. So I guess, well, Brad, you said this is actually happening, so we have a subgroup or subgroups that are going to attack this. See a little more emphasis on this during conferences. Again, I'm kind of selfish here, I'll admit. This is what I want. But a lot of you might not. But it's all about me. And promote, and this is what I was talking about the interfaces, is to make this a point of emphasis. So we can start playing nicely together. Play nicely with Python, play nicely with R, play nicely with C#. In .NET, the non-Microsoft version, the standard, they eliminated C++. So why?
Your point about focus on interfaces to other languages actually goes along with clean out the Boost library.
Oh yeah,
Boost Python has been dead for a decade, and some of us found out the hard way.
Yeah, that's true. Yeah, that's right. There's Boost Python. So yeah, very good point. But yeah, this would also apply to Boost. Yeah, so yeah, make this a point of emphasis and put well-maintained interfaces in the Boost. And then I don't know if any of you are familiar with the R language, which is used a lot for statistics and that. What they have is a centralized repository for what are called R packages, and these come out of research. So a lot of times published research in math and statistics will be accompanied by an R package. And then if it meets certain requirements, it will be accepted into what's called CRAN. Some kind of effort like that on the C++ side would be great, so you don't have, Joe's linear algebra library over here and Kathy's PDE solver over here. You don't get, put something together which has met some level of standards that can be somewhat relied on. Okay. And that's all, folks. Thank you very much.